welcome to my talk. Thanks for coming. As you can see from the bottom of the screen here, I'll be presenting the work on behalf of a very large number of people that form part of the Reef Restoration and Adaptation Program Cooling and Shading Subprogram. My name's Dr. Daniel Harrison, and I'm from the Reefs and Oceans Research Cluster at Southern Cross University. So first, our motivation. This won't come as a surprise to anyone here at this conference, but the Great Barrier Reef is in trouble. And here it's just maybe a new way of looking at it for some of the audience, but I've simply plotted a linear trend line to the average global temperature anomaly since the Industrial Revolution. And I've also marked on there the recent contemporary mass bleaching events recorded on the Great Barrier Reef. As we can see quite clearly, we've passed a tipping point on the Great Barrier Reef where it's now possible for the reef to bleach in any hot summer. And we're seeing that more and more, and typically in most of these bleaching events occurred during El Nino years, when you can see the spikes on the graph here might be 0.2 degrees or so above the average global temperature. And we're increasing the temperature at a rate of about 0.2 degrees every 10 years or so. So the situation that we have now, a strong El Nino year, in 10 years' time, that'll be an average year, and a strong El Nino in 10 years' time will be another 0.2 degrees or so above that in a global average sense. I've marked on there as well, of course, the more optimistic Paris target range, which we no longer think we're very likely to be able to stick to. And after that, the temperatures are really starting to look quite incompatible with the future health of the Great Barrier Reef. And so the Cooling and Shading Subprogram is about looking into whether there are any engineering interventions that are applicable at scale by which we can help to mitigate bleaching damage to the corals by either cooling the water down or shading the corals so that they have less light stress and less bleaching even in the presence of warmer water. So we can look at the scale of these different ideas, and the direct cooling ideas tend to be fairly limited to small scales, maybe a colony or up to a snorkeling area. Some of the ocean albedo modification type ideas are probably applicable mostly over a snorkeling area, but maybe could be pushed up to the size of an individual reef. And then some of the atmospheric interventions might be applicable over a larger scale, such as the oil fogging or the seawater fogging, or the marine cloud brightening, which is applicable over regional scales only. And the reason that seawater fogging and cloud brightening are green in this figure is because they're the two interventions that we've been actively progressing in the Reef Restoration and Adaptation Program during this first phase of research. So what exactly is fogging? So the idea is to create a low-hanging sea fog just generated from seawater that would float low over the surface of the ocean, be dense enough to reflect a meaningful amount of light, obviously, and to be able to be dispersed over a large enough area to make it worthwhile. Generally speaking, we expect most of the benefit of fogging to come from shading. So even though the corals are heat stressed, by reducing the light stress, it's based on the hypothesis that the corals will be able to tolerate increased seawater temperatures up to a point if the light is reduced. And there's quite a lot of evidence that this works. The corals experience most of the stress. Everything sort of goes wrong for them at once. There's less cloud cover, so more light coming through. There's less wind stress on the ocean, so there are less waves and less reduction of the light on the sea surface. Suspended sediment settles out of the water column, of course, and so there's also greater water column clarity and therefore more light making it down to the corals. And we've done some research that shows that these periods of doldrums are when the water really heats up and a lot of the degree heating stress starts to build up as well. The question obviously is that going to be enough to then infer a greater survivability to the coral over a bleaching event? And how would you actually do this? So the idea is fairly simple. You take seawater, you use large pumps and you put it through nozzles that atomize the seawater, much like a sort of a misting machine that you might find at an outdoor concert or some outdoor venues. Although the difference is in those cases, if you're doing it with fresh water, the fresh water evaporates and you just get that evaporative cooling of the air mass. With seawater fogging, a lot of the water still evaporates, but the sea salt crystals are left behind. And if you target those at the right size for scattering light, then you can continue to shade for much longer than if you tried to produce a fog of fresh water. And so we've been working quite hard in the sub-program trying to answer that first question about how much shading is required. And this has been limited so far to tank experiments, both with under natural lighting and also artificial lighting. And just to summarize where we're up to at this point is that there's been a bit of research now and seems to suggest that 15 to 30% is sufficient to impart a bleaching benefit of up to about 6 degree heating weeks, or that, I should say, the benefit is still there at 6 degree heating weeks. It's not completely overwhelmed. The big question that we're interested in is really whether over a whole bleaching event extending over a summer, if we're just shading at a location during the doldrum periods when conditions are suitable for fogging, is that enough to impart a benefit when you look at the whole summer in aggregate? And the answer to that seems to be yes, although we have some doubts about how transferable some of these results in tank experiments are to the real world. And so the next step's going to be to try this in the real world. And so we've, in parallel to the tank experiments I've been describing, we've been developing a proof of concept system to allow us to get out in the field and just to look at whether you can even really generate a seawater fog, what sort of size droplets can we produce, how much shading does that impart. And the results so far are fairly encouraging. We can make quite a large sea fog, which you can see there during a trial last year over the Great Barrier Reef. And that fog that you can see there, the average shade from boats doing transects back and forth under that fog was around 10 to 20%, a maximum of up to about 27%. Now, I'm not going to present too much more on the results of fogging because they're covered in a couple of other talks coming up this afternoon. So make sure that you see Joe Alroe's talk if you're interested in fogging. He's going to go through the entire fogging project from start to finish. Our droplet size is far from what we believe to be optimal. So we think that there's still a lot of scope to tune the technology to achieve quite a lot more shading and hopefully over an even larger area. We estimate that it's probably practical to go out and fog now with a couple of barges, a similar size system to what we tested there, but split amongst more sources, probably up to order of 10 hectares or so. So the next intervention that we've been looking heavily at, and I'm sure you've heard of, is marine cloud brightening. And so the fundamental idea here is that every droplet in a cloud, it needs a nucleus to condense around. Over the ocean, when the air is very clean and free from anthropogenic sources of nuclei and free of anthropogenic, well, not just anthropogenic, but also natural sources of nuclei like dust. Essentially, a nuclei can be just about any aerosol, which is just a small particle floating in the atmosphere. That's all that word means. Over the ocean, most of the cloud condensation nuclei are made up of either sea salt or sulfate-based compounds that have undergone chemical transformations for example, the release of DMS by phytoplankton or even corals themselves. So over the ocean, if we're away from the land, we have typically very low concentrations of these cloud condensation nuclei, mostly either sea salt formed from breaking waves. But the important point is that over the ocean, there can be very, very low numbers of these. And since every droplet in a cloud needs a nucleus to condense around, we get clouds that have the same amount of liquid water because the amount of water vapor is set by larger meteorological processes. But that amount of water vapor is forced to condense on fewer particles. And so those two glass jars there, they both contain perfectly clear glass spheres, but because the one on the right, the size is closer to the optimal scattering, the optimal Mie scattering size of light, it reflects more light back and appears whiter. Basically, we're looking at artificially enhancing that natural generation of sea salt aerosols over the ocean by taking seawater, much like in fogging, but atomizing it to a size of droplet that's about 100 times smaller and much, much larger quantities, orders of magnitude higher quantities than we're fogging. And when those droplets evaporate, the nano-sized salt crystals left behind form cloud condensation nuclei. And so essentially for cloud brightening to work, to be effective, we sort of need two things. We need the background number of cloud condensation nuclei to be quite low, and we need suitable cloud formations to influence. And so that's what we're looking into over the reef. So I said that was the simple explanation. I don't want to spend too much time on this, but cloud microphysics is immensely complicated. And when we're adding these additional sea salt aerosols, there's a whole chain of processes that could be impacted. And so one of the ways we can look into some of these questions is through cloud microphysics modeling. And we're doing this across quite a range of scales in the sub-program. So again, to start in the bottom right, you can see there the modeling at the scale of an individual experiment where the ship is releasing a plume and we're looking down on it there. So looking at the spread, and the panel to the right here is showing that sea salt aerosol plume released from a ship, and the blue is the clouds. And so it's looking at where the plume interacts with the clouds to brighten the clouds. And that's at the scale of an individual experiment. If we look over at the right, this is looking more broadly at a region over the Great Barrier Reef and trying to test the sensitivity. Are the clouds over the reef sensitive to cloud brightening? And the answer is yes, quite sensitive in this model. And one thing that's interesting to point out is because this shows really quite clearly that we're not making clouds when we look at this cloud brightening technology. We are brightening the existing clouds, and you can see in the cloud albedo here that the change for an individual cloud is fairly subtle. It's filled in a bit more and has a higher average brightness. And then, of course, the scales also extend through to looking at the larger Australian region there, and that model scenario there is looking into risk. And so this is looking at a cloud brightening scenario over the Great Barrier Reef and looking at whether it was likely to change precipitation over the Australian region. And the answer, at least in that scenario, was not really. Here, we ran a set of scenarios through the Reef's hydrodynamic biogeochemical model. And I just want to really point out two things. I'm only showing one scenario here where we assumed that we brightened the whole reef out to the edge of the continental shelf. And you can see that the cooling is really quite limited to the region over which you're conducting the cloud brightening. And this is a bit of an unusual case, and this is also the reason that this idea could actually work for the Great Barrier Reef, is that we have a large shallow lagoon. And we can see that here if we look at the baseline and the cloud brightening scenario here. I apologize, I've just realized they're labeled backwards, but the blue is actually the cloud brightening scenario and the red the baseline. But the water is essentially captive for a period of time, the residence time within that shallow lagoon, and just like a shallow lens of water on a beach on a hot summer's day, it heats up quite quickly during these events that cause the coral bleaching, especially when we have low cloud cover. And when we run the model and we increase the brightness of the clouds, you can see here that the residence time is reflected. So it takes around 2 weeks or so in this particular scenario for the temperature with and without the cloud brightening to diverge. But then after that point, there's sort of a balance reached between new water coming into the lagoon and cooled water, if you like, or water that was prevented from heating up, flowing back out of the lagoon. And another thing that we found with this modeling is that you can fairly reliably predict if you have a given amount of average reduction in solar radiation, the amount of cooling that you'll get. And we ran here scenarios with both assuming that the low clouds that were actually present in these hindcast scenarios were brightened, but also looking at an equivalent amount of forcing just applied evenly everywhere over the scenario area. And you can see here that the difference between those scenarios is the circles and the squares. And you can see that they all lay on the same line, essentially. And so that's quite interesting. And that means that the movement of the clouds over the length of the scenario, which is a couple of months long, and the circulation of the water even out any irregularity in the actual exact location of the forcing, at least on this scale. And then on the right here, because Eyre Reefs has a biogeochemical component, we can actually model the combined reduction of stress from light and temperature in the corals. And we're updating this modeling at the moment, but we previously did this work. We did it over those two initial bleaching events in 15-16 and 16-17. And what we found was that in 15-16, which was a strong El Nino year with less cloud cover, there was still a benefit from cloud brightening, and bleaching stress was reduced about 50%, but not as much as the following year, which wasn't a strong El Nino, and the cloud cover was higher, where it was about 65% or so. So some colleagues at CSIRO then took some of these results and put them into models that play the ecological models, COCONET in this case, that predicts ahead over time the coral cover on the Great Barrier Reef based on an ecological model. And so again, these are scenarios that assume that the cloud brightening was effective. They assume that you were able to actually brighten the clouds. And what we found was that consistent with our understanding of how things work, there's only a certain amount that you can brighten the cloud. So you can't just keep doing more and more cloud brightening and getting more and more reduction in temperature. If you had some of these effective cloud brightening scenarios operating over the whole reef during the bleaching years when you needed them, and you also had really strong action on climate change, the so-called RCP 2.6 scenario, then the sort of baseline predicted trajectory in this work that's quite dated now is the dashed line here, and the solid line is with cloud brightening. And so you're able to avoid some of the degradation of the reef by applying the cloud brightening intervention on a very large scale, of course. However, what we also found was that under a more business as usual type climate pathway, you still get that benefit, of course, but that gap that you can exploit in the clouds, it eventually becomes overwhelmed by climate change, and you just can't keep up. There's no more gap to exploit. And so this is very, very strong evidence that, or a strong reminder, if you like, that these interventions, they're really only going to be effective if they're combined with very strong action on climate change. They're no silver bullet on their own. But when we put all of this modeling together, what we end up with is a sort of number of about 10 to 20 watts per meter squared average reduction over a bleaching summer, and that appears to be enough to alter the trajectory of the Great Barrier Reef going into the future. So that then, of course, raises the question of whether we can get 10 to 20 watts. And so that's where most of our research is focused now. And so this is looking at a typical field experiment we've built up over the last few years, from initially testing the equipment that we use to generate the sea salt aerosol spray to atomize the seawater, then looking at the dispersion of that with drones, then introducing an aircraft, and now we're at the point of starting to look at how those sea salt crystals that we're generating are actually interacting with the cloud microphysics. And there was a whole heap of engineering that had to go into this, to getting to this point, obviously. And I'd like to point you towards Chen's presentation later this afternoon, where he's going to go right through the engineering from the very, very early days to where we're at now for the cloud brightening technology. The other challenge that we came up against was that there was no cloud microphysics research capability in terms of an airborne platform in Australia. and it was going to take too long and be too uncertain to try and get one in from overseas, as well as expensive. And so we actually ended up starting from scratch and developing our own, and that's been quite exciting. And Peter Butcherine is going to give a talk this afternoon about some of the exciting remote sensing capabilities. He's not going to go too much into the cloud microphysics for this particular conference, but he's going to talk a lot about the bathymetric LiDAR and the hyperspectral imager that we've been using in our research in this sub-program. And just to give you an idea of what this actually looks like, I've chosen a video here from a not particularly cloudy day, but that's so that you can nice and clearly see the vessel and the plume here without it being hidden by a whole heap of clouds. But you can see us flying up on the sea salt plume here, right where it's going into a very small cloud. And most of the instruments on the aircraft there are designed to sample optically as you go through, and they're measuring the size, distribution and concentration of those sea salt crystals that we've produced, as well as the size, distribution and concentration, of course, of the cloud droplets. So one of the questions that we had to look at in this research, there was some literature out there suggesting that as the seawater evaporated to leave these sea salt crystals that we want behind, that would cool the air mass, much like the misting at the pub, and that would prevent mixing of the sea salt aerosol plume up to cloud. So we've quite thoroughly dispelled those concerns now. So the bottom plot here is upward pointing LiDAR. And so you can see the cloud layer there. Sorry, the bottom axis is time. The y-axis is height. And you can see the cloud layer, the dark red layer there, and you can quite clearly see our sea salt crystals lifting up to cloud base there. And I should mention, by the way, both in the LiDAR data and also in that visual imagery that I just showed you, you can only sort of pick up less than 1% because the sea salt crystals are nano-sized. It's the very few larger ones that are actually larger than what we want that you can actually see optically. So although even that plume coming out the back of the vessel might look quite impressive, 99% of it's invisible. But not to our instruments on the aircraft, of course. And here at the top, these are plan views, so like a map view of the sampling just below cloud base. And these are just illustrating that they're getting quite high concentrations of these sea salt up to cloud. And so that sort of box was ticked. This is very hot off the press. So in the top right panel here, the red clouds are seeded with our sea salt aerosols from the vessel, these cloud droplet radius again, and the blue are the clouds that were right nearby but outside the influence of the plume. And in this case, we saw about a 2 micron decrease in cloud drop effective radius. So about half of what we saw during that natural experiment, but that natural experiment was a very, very large event. Nevertheless, it shows that there's possibly still room to optimize the technology to get even more brightening of clouds. And the panel on the left here just shows the full size distribution as opposed to sort of the mean effective radius. And you can see here quite clearly the difference between the seeded and unseeded clouds. That you've got the similar amount of water inside the cloud, which is the integrated area under the curve, but there's a crossover point. We've shifted the size distribution from larger to smaller, which is consistent with what we expect in that first Toomey effect, that immediate brightening effect of the cloud, which is what you saw in those satellite images. We can also see this and measure it by satellite, by the way, but I fear I didn't have enough time, so I haven't included it here. This research is being done with a very, I guess I'd like to say best practice or better than best practice level of governance and engagement. We have a board and steering committee, independent risk review group. All of the work's done within the Great Barrier Reef Marine Park, which is federally managed, and all the permitting processes for that mean that we have to have community engagement and community consultation, as well as traditional owner consultation. But we go beyond that in all of our RAP, and we actually seek free, prior and informed consent from traditional owners of the Great Barrier Reef before we do any research in their sea country. We're also participating in community panels, and there's Great talk will be given by Samantha about that at this conference. So in conclusion, with further technology refinement, fogging appears to be feasible over areas of up to 10 hectares or a couple of maybe 20 hectares. The next steps for fogging are a longer running experiment. In the initial phase of our app, fogging was really very much proof of concept. Is this even feasible at all? I think we've shown that it is, but it's applicable to fairly small areas, unlike the cloud brightening, because you need to pump and atomize so much more water. For the cloud brightening, we're fairly confident. I think now that the target is around 10 to 20 watts per meter squared of average solar radiation reduction over a bleaching event. We've shown pretty convincingly, I think, that the dominant summertime clouds over the reef are susceptible to cloud brightening, but we still really need to get a handle on how different states of the atmosphere, different types of clouds, different background concentrations of cloud condensation nuclei, how they affect the amount of perturbation that we get in the cloud. And we've developed the technical capability now to do those experiments. We've just completed a much larger set of experiments this year, which will give us some insight to those questions, but we don't yet have the results fully available. And finally, and very importantly, that emissions reductions are an absolute prerequisite for preserving the reef. It's not an either or, it's an absolutely, we need every tool at our disposal kind of situation, in my opinion. And so finally, I'd like to thank all of the members of the sub-program, as well as the wider RAP team that have just been working so hard on looking into these interventions for the Great Barrier Reef over the last few years. Thank you.